Hello, this is the last lecture of this week where we are focusing on designing using selection maps, what we call stiffness maps, inertia maps, feasibility maps, and using spring lever model as well as spring mass lever model. Today we will actually demonstrate this technique using two programs, one built in Matlab, other built in Java. Online one can access and try out this technique. So, let us look at the demonstration of the selection map based design technique for designing compliant mechanisms. So, let us start with a little bit of recap of what we have discussed before we go for the demonstration using software today. So, let us just write a few things down to see that we understand how this design technique is going to work. The first thing we discussed was this SL model. So, where SL is a spring lever model. So, this is spring lever model where we used three properties of compliant mechanisms. We do call them properties because they capture the effect of a compliant mechanism when you look at it from the terminal model. That is, there is a input terminal, output terminal, or you can call it input port and output port. Between the input and output, what happens is captured by this SL model for statics. That is, static response is what you are interested in. Then we have KCI, KCO and N. These are the three parameters which happen to be in the 2 by 2 symmetric matrix that relates input degrees of freedom to the input degrees of freedom in terms of displacements to the corresponding forces or moments on the other side. So, that is what a spring lever model will capture, more like a black box or terminal characteristic model. Later we also discussed SML model. So, this now becomes applicable for dynamics where we have spring and mass and lever model. So, here we add also MCI and MCO. If KCI and KCO are input side and output side stiffness parameters, MCI and MCO are the input and output side inertia parameters. So, these 5 quantities we also call them properties, because every compliant mechanism has some property just as a material would have its properties. For statics there are three properties, for dynamics 2 more properties. So, these capture what happens with the two terminals of a compliant mechanism that has one input, one output. If we have multiple inputs and multiple outputs, that will be different, but for a single input single output compliant mechanism, these 5 properties suffice. Using this model and based on user specifications and this model, we drew what we called feasibility maps. In fact, it is a projection where the n value is actually shown like a grayscale density in that feasibility map. So, there is some map like this. So, inside this map, any point that you take is going to satisfy the user specifications. User specifications, we had a long list, rather 12 inequalities. We have input force and input displacement, output force, output displacement, and we had actuator stiffness, and we had also K external. So, all these things had upper and lower bounds. So, we specify all these 12 values. So, there is a lower bound, upper bound, lower bound, upper bound and so forth. So, these are the 12 ones are the ones that user specifies. Based on that, we draw this feasibility map and find the feasible values of KCI, KCO, N if it is a statics problem. N of course is shown like a gray density. in this map. Otherwise, if you take 3 axes KCO, KCI and N in a 3 dimensional space, it will be a volume. That is what we discussed. Once that is there, at least the user can be guaranteed to believe that there is a scope for finding a solution for that. Now, what we do is we look at the compliant mechanisms and try to put them as dots in this map. So, once we have this feasibility map drawn, let us say it is something like that, this is the feasibility map. Now, every compliant mechanism, now this is let us say KCI, KCO, sometimes you may want to plot KCI and N, depends on the application. So, in the 3 dimensional map it is a projection, then every compliant mechanism will be a dot. So, some may be inside, some may be outside. Now, we say if CM1 and CM2 are inside the feasibility map, they are suitable for the application. Let us say CM3 is here, which is outside, which does not satisfy the user specifications. So, it is more like selecting a compliant mechanism database. This is for statics we discussed. That is what we will demonstrate with a software program today. In fact, 2 software programs will demonstrate how we can specify these 12 values here, right. So, there are 6 variables and each of them have upper and lower bounds. We can specify them and try to construct this feasibility map. We have discussed how to compute it. Once we have that, using a database of compliant mechanisms, we can get all of these compliant mechanisms plotted here and then see how many of them lie inside, how many of them lie outside. If any of them are lying inside and the corresponding n value also satisfies or rather within the range, because once a feasibility map we have KCI, KCO here, every point will have certain range of n values that is continuous as we have discussed, and that continuous range of n, if it is also matches with the compliant mechanism, let us say at this point there will be a range of n and the n of the compliant mechanism, which is what we call property, lies within that range, then this compliant mechanism satisfies the user requirements completely and we can take that. If it is not and none of the things that are inside actually match the n value also, we go to something that is not inside and try to bring it inside by drawing some parameter curves. So, we vary various parameters like the width of the beams, overall size in x and y, change material, change the x and y sizes simultaneously or cross section and this simultaneously. We can generate all of that and get it inside. Once it comes inside, we may find that that satisfies, and again we have to satisfy n value. So, we can also do the redesign. So, while designing that, we can look at the strength as well as manufacturing considerations such as minimum width of the beam that can be made using a process that you can select. You can actually select manufacturing processes and then set specifically the manufacturing process also in there in terms of size, thickness, narrowest beam, widest beam and smallest hole, all that can be specified, and accordingly we can redesign and then get something that actually comes inside the feasible space, satisfies the all other requirements, manufacturing, strength, of course functional, stiffness, displacement and force, that can be done. This is for statics. If it is dynamics, what we also said is that in addition to looking at the stiffness map, we can call it stiffness map when we are plotting KCO versus KCI. Similarly, we can talk about inertia map when we talk about MCI versus MCO versus MCI. So, there will be something here, there will be something else here. Now, when I click somewhere here, there will be n value, correspondingly there will be an MCI, MCO, because of the user specifications. In this case, in addition to input force, input displacement, output force, output displacement, actuator stiffness and external stiffness. We might also have dynamic considerations such as natural frequency or time for certain task. Some, let us say it is a valve problem we discussed, the valve should open within some time. All of those dynamic considerations can be kept, and user can specify if it is like time to open. So, T open, user can specify a lower bound and upper bound. There will be more equations for us to solve in terms of now constructing these two maps. The stiffness inertia maps, whenever there is a cursor, if it moves from there to, let us say, to another point, let us say from there to it moves here, this might move here, you have to do that, it may move out also, right. Again we show all the compliant mechanisms on both the maps. So, there will be some inside, some outside. So, we have to look at all of those and do the same procedure as we have done, and that way we can select compliant mechanism from a database and modify them or redesign them. If something is not there, we can draw these curves that bring it inside and satisfy the user requirements. So, that is how it is going to work. All of this we have discussed so far applies to small displacement compliant mechanisms, meaning that instantaneously that is what the properties that they have, that is spring lever model and spring mass lever model, both are for instantaneous behavior of a compliant mechanism. But compliant mechanisms are known to undergo large displacements. So, we need to consider that non-linearity also, meaning that if I have a compliant mechanism and I want to consider the large displacement behavior, if I want to plot KCO versus KCI, KCO versus KCI, it will be a single point if we consider instantaneous behavior of the compliant mechanism. So, at that instant it has one KCI value, one KCO value. Now, when you start applying more force, then its stiffness is going to change, most often because of geometric nonlinearity, not because of material nonlinearity. Due to geometric nonlinearity and sometimes even including contact, we will have change stiffness of compliant mechanism. So, when there is a change stiffness, because if you again recall this KCI, KCO, N are nothing but this 2 by 2 matrix, it is symmetric, input displacement, input output displacement, and then that relates input force and output force. So, these 4 things, because symmetric matrix, so these are basically representing our KCI, KCO and N, right. Now, this is going to change because as a compliant mechanism undergoes large displacements, this matrix which we call tangent stiffness matrix, at that instant what happens, because there is no force, it is under no force load free condition, at that point we have KCI, KCO, N. Now, when we deform the compliant by applying some force, it is in a different state. At that point again we have to construct a linearization to relate displacements and forces from that configuration. So, all these values will change. So, they will change with deformation of the compliant mechanism, with the deformation of the compliant mechanism that we are considering. So, this is what we call nonlinear or large displacement compliant mechanism. If that happens, then KCI, KCO values are going to change, right. It is going to go from one point to another point, at different points you take, these all with one compliant mechanism. There will be a path for it, there will be a locus. Now, this will still be amenable for our feasibility map technique or selection map technique. If let us say a feasible map is somewhat like this, then we will know that if we are starting here and as you apply more force on the compliant mechanism, its KCI, KCO change like this, we will know up to what point the compliant mechanism is going to meet the requirements. The user also has to specify input output displays maybe from initial to final, So, final is here, initially it may be there inside, when you apply, that is basically 0 force, and that it may be inside, but as you apply the force, KCI and KCO, the mechanism are going to change, it may end up here. So, it does not satisfy, but up to what point we can satisfy we will be able to know. So, the concept of selection maps with stiffness maps, inertia maps, both are feasibility maps. We can now draw a curve corresponding to each compliant mechanism when you consider large displacements. So, this concept of selection map based technique does work when you have large displacements, or read it as nonlinear behavior. It will still work. The difference is that each of them will not be a point, but there will be a curve. That may be curve like that, this may be curve like this may be curve like this may be curve like that. So, the things are going to change, each of them will have, and you have to work in the same way. Same thing inertia and stiffness maps as well. So, the concept works for large displacements also, right. So, what we will do now is these are the two papers that we have repeatedly referred to in this week's lectures. You can read the case studies that are there. We had one lecture on the case studies as well. Now, let us look at the procedure of designing compliant mechanisms using this technique by using a software. So, what we will do is we will first look at what is implemented in a Java program. So, I have a recorded movie of that. This is available to you as part of this course, because you can actually take it from the online URL, Universal Resource Locator, but just look at how it works. So, this is a movie. So, first I have to pause and show you what happens. So, first let us start. So, when you start, there is a small print here, but you can read on the screen. There is single point and 2 point. What this means is that single point means that in a compliant mechanism, there is a database of compliant mechanism. In all of them, there are input points and output points. All of them are already prescribed. At the input point, because they are all 2D, there will be 2 degrees of freedom. There is a x displacement and a y displacement. So, if your input output are both at the same point, then that is a single point you choose. There may be applications where you want input output both to be at the same point, but in different direction. That is, you are pushing in one direction, it will also get pushed other direction. So, this is your input, that is your output. In a 2.1, there are of course 2 different points, and you can choose input at one point, output another point in whatever direction one prefers. Okay. So, most often it will be 2 point compliant mechanism. So, we can click that and select it. So, that is the first thing to do, and then what you see here in this little block here, it has the 6 parameters we talked about: input force, input displacement, output force, output displacement, actuator stiffness and external stiffness, lower bounds, upper bounds. Units are indicated here, but one can follow one's own consistent unit system. So, I will just run it now to see that one can enter all these, they are already entered, and then if you say confirm changes, then it would actually draw the feasibility map. Now, confirm changes is clicked, now it actually draws the feasibility map. I mean, the other lines are not visible, but you actually get a feasibility map. By zooming out, you can actually see the feasibility map. That is here KCO and KCI, and we have a feasibility map drawn. So, if we change any of these numbers, feasibility map will change. In doing so, we are solving those 12 inequalities, upper and lower bounds and the 6 parameters, and the 2 equilibrium equations pertaining to the spring lever model. It is all done for statics. This program is only for static applications. So, we have the feasibility map drawn here, and then you also see a little dot here. That is actually because we are selecting one best mechanism which is inside the feasibility map or closest to it. You can change the number over here to see more and more mechanisms. So, if it is there, so that will be visible, and if you double click on it, it will open a window where that mechanism will be shown. Correspond to that point, we said there is a database and you are showing the closest mechanism that is in the feasible space or closest to it. Then you double click on it, the mechanism design will be inside. So, you can see the animation. At this point, user can see whether that is suitable for the application or not. And if you select some more, let us say 20 are put, some more mechanisms are shown, you can zoom in and select anything else that want to see how does it look, because many of them are inside. So, it is a different one now, they are different, it is a suspension here. So, a different one shows up. So, you can choose this mechanism and then see which one of them lies. Remember that all of them have two different points, input output can be interchanged. Once you have a database, you can have multiple ways that you can look at. Input output can be reversed and that may look like. You can change the numbers that is being done now, and then confirm changes. If you do, then it will redraw the feasibility map. You can see that the shape changed because numbers are changed. Again, you can mention how many mechanisms you want to see, whether lying inside or not, and look at the mechanism and see if its n is satisfied or not. It is a different mechanism now. The animation tells you where it is fixed, whether how many fixed points are there in the mechanism, and all of those details one can take. So, is again being shown that 2-point confirm changes with some things, goes back to the specification we started out with, and that is how we can do this mechanism. So, we can change the specifications and work with it. Now, what we will do is look at the redesign as well. Now, we see user need to simply enter the specifications and then feasibility map, look at the mechanisms and look at their animation, and then see whether that mechanism will suit the particular application or not, and choose the mechanisms. If none of them are satisfied, we have to go for the redesign. That is what we will show. This is a redesign. Again, this is 2-point, we are confirming changes, got that, and look at the mechanisms, all mechanisms, everything will be shown here. 5 is entered. So, some of these dots appear, and you look at the one that you like, just to bring you like it, whatever reason this mechanism looks a little sketchy, but after all it is in database, that means that somebody has entered, it is a valid compliant mechanism, and that is lying outside the feasibility map. You need to bring it in by changing. So, that is what we will see in this movie clip. So, you can see how it deforms, and now we see to bring it in, you choose CNC milling, that is what we have. So, look at that, we have chosen CNC milling. Other options are wire EDM, lithography, that is microfabrication, and then metal etching, laser cutting. We have chosen CNC milling. It opens a box like this where you can put minimum gap, minimum width, minimum thickness, maximum thickness, minimum size in x and y, and maximum size in x and y. You can enter all of those values in this units that you are consistent. Once you OK it, when we change these parameters, we have now in plane width, thickness, size in x, size in y, material, and all of them at once. If we do, it will do that. Now, we will continue with the movie clip. So, in this particular case, we are choosing decreasing the size, then that particular thing will have. Decrease the size going away from the feasibility map. You realize that decreasing size is not an option for this particular case, then you change, maybe increasing size would work. Instead of that, let us increase size, then it goes the other way, comes back into the feasibility map. This is exactly what we mean by redesign. We are not redesigning the topology entirely, we can see what mechanism it is. Here this is the mechanism, and we are increasing the size of it and try to get it into the feasibility map. You do not have to do anything more. Of course, when this locus is being drawn, lot of finite element analysis are being done, lot of finite element runs are being done within this environment. In this case, it is a Java environment, and it is just getting you into the feasibility map. After that, you have to match the n value also. So, now if you click any point on that redesign curve, now you see in this particular case n range minimum is 6.34, and maximum is 8.64, and the mechanism point at that thing has 8.68, maximum is only 8.64, whereas you have 8.68 and that is in red color, meaning that n does not satisfy. So, you have to explore more along that curve, it is a redesigned curve. If you go somewhere else, now it suddenly became green. So, maximum here is 7.77, this is only 7.26, minimum is 6.38. So, now you have green, you are done, you can take that mechanism and walk away. So, that is how it works. Of course, you can look at maximum stress and look at the mechanism one more time how it looks and so forth. So, that is how we do the redesign of the compliant mechanisms in this technique. What we will do now is we will switch to a Matlab version and look at that. So, that Matlab version, online version with the URL given to you, you will be able to access it, and with Matlab version you will have more control. If you want, you can even change whatever you want, add more things to database of the compliant mechanisms that is integrated in the program and play more with it. So, let us look at the Matlab version of this same technique. Okay. So, in the Matlab version we have a program, as we can see, it is actually called interactive chart. That is what it is, because this whole technique is interacting with the user right from the beginning. The user wants specified numerical quantitative values, and that is a distinctive feature of this technique. The user can actually specify the values and try to run. So, if I go and say run this program, then it will come up with this the chart. So, this window, what we saw in the Java program, similar structure, the input here and showing mechanisms and so forth. Let us say I change this value, it is now 250. If I change to 300 and then say show feasible map, it changed, and I can let us say decrease it. I will decrease it to 150. So, input is between 100 to 150 things here. If I say feasibility map, it did change, something happened here. So, the shape changes. So, we can enter the values the way we want. Let us say output is now 2 and 3, let us say 2. If you say precisely you have only 2 newtons of force, then you can put 2 in the input output and show the feasibility map. Now, it becomes more or less rectangle, here it is little curved. So, if you want to zoom in here, there are zoom buttons here for this graphics window. We can actually see the zoom in there, and just like in Matlab, this is actually based in Matlab. You can actually look at that, double click bring you back to this. Here there is no external stiffness. If you want to put external stiffness, you can put, let me put 100 and 120 here. Now, say feasibility map, suddenly it goes, or rather it will become, in this case, very small. Maybe I have to zoom in a lot to see that, otherwise just a line. So, that means that this specification may be a little too harsh, that it just a line is the feasibility map, right, and then KCI is something like 0.1 and KCO is very large, because in order to have external stiffness to be handled, you need to have very high stiffness on the output side, become 10 power 4, that is 20,000 or rather 15,000 here, whereas this is only 0.1 because input displacement like that. If I increase the force, let us say, so in order to counteract that, let us say I go from 1000 to 1200, that is I am using a different actuator. Let me put that feasibility map, now something comes, the shape is more interesting. So, now we can see that if your output load is more, output stiffness is more, even if the feasibility map has reduced, means that your specifications cannot be met in practice. Now, you have to use a different actuator. So, that is what we have done, different actuator, but displacement, let me increase that also, let me make it instead of 0.001 which is a millimeter. So, now let me make it a centimeter, and I would say anywhere between 1 centimeter 1.5 centimeter I have an actuator, let us say that directly comes from the actuator. Then feasibility map, if you show, it changes. So, now I get, let us say little ambitious, I want let us say more displacement, I want 2 centimeters, right, precisely input output lower and lower bound upper bound of the input displacement I put 0.02 here, I still get in fact little wider things. Then I want to see how much displacement can actually have, because actuator stroke will be there, it is a 5 centimeters feasibility map, it even widening, right, giving more displacement is actually getting it better. So, then I would see what happens if I use a smaller actuator, let us say I put only 500 newtons, now 500 newtons to 600 newtons. All the specifications are compliant, right, so they are flexible in a way that there is elasticity in the value that user can specify. So, if I say feasibility map still fine, then I can see what is the smallest actuator that I can actually take, maybe 300. If I take 300, what happens to the map? So, now it became narrower. So, we can see that as I change the values, what is the actuator? Let us say that if I show compliant mechanisms, now we have to see that they are all somewhere. I have to really zoom in now the thing. So, we have to see where the map will always be at the origin. So, we have to zoom in a lot, meaning that whatever we have in the database we do not have. So, let me keep on now we see the map here, little green one. So, nearest compliant mechanism is over there, right. So, if I can use these draw parameter curves and get it inside if you want to go with the smallest actuator. So, here while designing compliant mechanism we can design it for the actuator the user chooses, and there are other features that we saw how to get it into the feasibility map by changing this, the manufacturing processes, we can look at the stress as we go along, and manufacturing process we can customize, and into the size also we can choose what is possible and get that here. So, this Matlab program gives a lot of flexibility, and the more things you add into a database, the more the chances that for a specific that user enters there will be a compliant mechanism that is readily available for that application, suitable application. If not, we can change it and get it in there. Once we get that, we can add it back to the database and make the database richer. So, that is how this technique works. Thank you.